going to pick one variable to manipulate and then figure out how you can make everything else the same. Right? We're trying to isolate our variable. We just want to test one thing. Does that affect the rate? What data are we going to collect? What are we going to keep the same? What's our control experiment going to be? Then we learned the rate law, that you cannot tell from the equation which reactants are going to affect the speed and if they're going to affect the speed equally. We need experimental data to do that. So we talked about order, we learned how to calculate the constant and the rate law in general. Okay, the next thing we're looking at is something called the integrated rate law. You don't have to have calculus. This class, calculus is not required, but it is from an integral, taking an integral of something. We're just going to look at 0, first, and second order because they really just want you to memorize. Actually, they're on the equation sheet of what those would look like if you integrated that rate law. The rest you need to know calculus. So we're going to take this a step further, and we're going to look at this time dependence. And to do that, you need to take a little bit of calculus on it. So using calculus, that's all they say. You don't have to worry about how to do it, just using calculus. To integrate, if you had something that was first order, this is what you would get. Brackets mean concentration. That's your natural log. And this is your original concentration of whatever you're dealing with, right? If it's first order, it just has one concentration that it depends on. And this is after time, whatever, 60 seconds, 2 years, whatever. So T is time, and this is that little constant that we figured out, right? From last night, we learned how to just take a trial, plug it in there, and get that. So this is the integrated rate law for something first order. If we rearrange this, and so the new things, that's original concentrate at time 0, after time whatever, K is our constant, T is whatever time. If we rearrange it, we can get it into a y equals mx plus b format, which is really helpful for collecting data and see if you have a linear relationship. You can tell if something's first order, second order, or 0 order. If it's a first order and you graph time on your x, and you take the natural log of the concentration at all these different times, time being your x, natural log of how much you have at that time as your y, and take a bunch of points and graph it, and you get a nice r squared equal to close to 1, then you know, oh, it's first order. Beautiful. And we'll see that on the next few slides. You can find graphically what your K constant is, because negative K is equal to your slope. So therefore, if a reaction is first order, if you graph natural log of concentration and time, you'll get a nice straight line with a nice r squared close to 1, and your slope is going to be equal to your negative rate law constant. So that'd be super helpful. And this is what we're going to do in next week's lab. We're going to use the colorimeter, and we're going to do we're going to take the known concentrations of something called crystal violet, like our normal, get a calibration curve, so that we can get concentration. And then we'll do the actual experiment where you add NaOH and crystal violet, and it gets more clear over time. And so that way we can use absorbance to get concentration. We'll do the concentration versus time, graph it. We'll do natural log of your concentrations versus time, graph it. And then we'll also do the second order, which we'll get to here, and see which one had the best r squared. And then you can tell what order that reaction is. That'll be next week's lab. So if we look at this reaction, methyl isonitrile, so just one reactant, we want to figure out, is this 0 order, first order, second order? It could be more than that, but it's beyond scope of this class because you need calculus for that. So we're doing 0, 1, or 2, and we're looking at integrated rate laws. So if we look at this, we take some data, and this happens to be a gas, and pressure is proportional to moles. So we took some pressure units. It started high and it went down. So I'm looking at the reactants here. So here's your data at this temperature. So there's the temp. Over time, the pressure, this went down, meaning the concentration, right, went down for moles because this was getting consumed and this was being made. We just happened to measure this one. And for your lab tomorrow, you can do reactants or products. And we'll talk about that. Maybe you want to do mass. Because if the gas is one of the products, if you just like leave it open, the mass of your reactant should go down over time. Because those, yeah, and we'll talk about that after this. Anyways, okay, we're looking at reactants. We did pressure because it's a gas and it went down over time. Okay. And you can use pressure or concentration when you're looking at gases. So this isn't very straight. We wouldn't get a great R squared here. So it's not zero order. Let's try taking the natural log of all those and graphing that versus time. Oh, that looks great. This must be a first order reaction. So that's what we're going to do in our lab next week, is we're going to do this crystal violet NaOA reaction and collect some data and graph it and see if it's zero, first, or second order. And the closer the R squared is to 1, that tells you which relationship it is. And so this is first order. We can also calculate what the constant is for this one. We take the slope, whatever that number is, make it equal to negative x, divide the negative on both sides, and for this one we got this. And if it's first order, you know it's seconds negative 1. If it's second order, it's molarity negative 1, seconds negative 1. If it's second order, if we took the integral of something that's second order and rearrange it, this is what its y equals mx plus b would look like. Your y would be 1 over concentration, x is still time, and your k is whatever your slope is. So if, this down real quick, I'm going to go back real quick. If I graphed this pressure versus time or concentration versus time, either one, not quite right. Okay, it's not zero order. All right, let's try natural log of each of the concentrations or natural log of each of the pressures. And it kind of looked, it didn't look like this. It was a little more like, bleh. All right, it's not first order. Let's do 1 over each of the concentrations versus time. And then if you get a nice linear, okay, it must be second order. Great. It's a second order reaction. Whatever my slope is equal to my rate law constant. So we'll see. Oh, here it is. So if a process is second order, then you plot 1 over the concentrations versus time, and you get a nice straight line, and the slope is equal to k. Yeah. And these are really helpful when we're looking also at half-life. Okay, so there's those, and we will put these on the piece of paper here in a second. Oh, here's our second order. They did this reaction. We already knew that other one was first order, so let's look at a different chemical change. We have this NO2 decomposing into NO and O2 at 300 degrees Celsius. We took the concentration of your reactant every 50 seconds. Bam, 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 bam. It goes down. That makes sense because it's making more products. If we graph this and this, we should not get a straight line. If we graph this and the natural log of each of these numbers, we won't get a straight line. And if we graph time and 1 over each of those numbers, then we should get a straight line and know that it's second order. And that's exactly what we're going to do in our lab next week. The data collection for it's really good. So, okay, well, that's exactly what we did. Natural log of each of these, not so much. Didn't work out. So it's not first order. Not a straight line, so it's not first order. Let's try 1 over each of these. Yay! Okay, it's second order. And again, we saw there's 6th order, 5th order, there's a whole bunch, but as far as we're just going to keep it up to 0 to second, since calculus is not required for this class. But this stuff is coming from calculus. Questions so far? All right, cool. All right, let's look at half-life. All right, so half-life is how much time for your sample to be 50% gone, 50% of it to react. So you can see here, this is a half-life. This went from 150 to 75, 75 to 37.5. So how much time to go from here to here, from here to here? That is your half-life. And half-life is a different equation, whether it's 0, first, or second order. So if it is, yeah, okay. What else was I going to say about that? If it's a 0 order, which is kind of what we saw your sophomore year, it's just 0.5 times your original. Oh yeah, so this is the definition, sorry, of a half-life. How much time to get half of your original. But this isn't a half-life equation. That's just like a definition in mathematical terms. If we want to know how much time it'll take to break down 50%, we take our integrated rate law for first order, and we get this. And this, I think, is on our AP sheet. So if it's a first order process, the half-life does not depend on how much you start with. You'll notice concentration is not in this equation at all. It's just based off your constant, K constant. And that'll tell you how much time it takes to go down by half. If it's second order, right, here's our integrated rate law for second order, rearrange it. Now it does matter how much you start with. It's going to be 1 over your constant times your original concentration. That'll give you your half-life. So for this, you just need to know, is it first order or second order? And then you can apply the correct half-life equation, which can be really important if you want to know how much pesticide is around after a certain amount of time, or how much like a byproduct of a medication over time, if we know the half-life. But we need to know, is it a first order reaction, second order, and then apply the correct equation. Second order, it does matter how much you start with. First order, it doesn't. Okay, let's switch gears to the Elmo. And, oh, actually, one more slide. We'll go back to the slideshow. I want to do this one before we switch to Elmo. This is like a little glow stick, and that's a chemical change. The products is this light. As temperature goes up, this is in a warmer, this is in some ice water. So does the reaction rate, which some of you guys will pick that for your thing for tomorrow. This changes the K. So your K changes on which reaction it is, but also it's temperature dependent. Let's see. Oops, so sorry, I didn't move that. There you go. And you can see here your K's change as your temperatures change. So K is dependent on what you have and what temperature it's at. All right, let's switch to the Elmo and let's summarize kind of on one nice sheet these laws that we looked at. And I am going to go stop share. Let's switch videos to the Elmo. All right, so for a first order reaction, our rate law is equal to your constant times 1 reactant, right, to be first order. If we took the integral of that, we did a little calculus, it would be natural log your concentration of A at whatever time over your original concentration of A is equal to negative your rate law constant and whatever time. Now what's helpful for us, that's what's called the time dependent. Right, here's time now. Time wasn't in this. If you now wanted to look at after this much time, how much is left? Then we got to do a little of the calculus for integrals. Now let's rearrange it if we want to graph it and put in that y equals mx plus b form. It'd be natural log of your concentration after some time is equal to negative k time plus natural log of your original concentration. And I'm going to grab a different pen while you put it down. So now we're in what we love in the lab is the y equals mx plus b form. And our slope is equal to negative k. Negative k is your slope, so negative slope is k. So you can solve for your rate law constant in your graph. All right, what do we graph if it's first order? Natural log of all your concentrations and time. Natural log over here. And time, of course, in seconds down here. And if your R squared is close to 1, then that means it's first order. Which if it looks, oops, something like that. And the half-life equation, if it's first order, so your time to have 1/2 of your sample left is equal to 0.693 over your rate law constant. So when it's first order, your half-life is not dependent on your original concentration, whatever you started with. So it's important as a chemist to know what order it is, because you're going to have different time-dependent equations. And so if you want to know how much stuff is hanging around, you want to apply the right equation.
Sportio, what does that say in the margin?
R squared close to 1, and that means it's first order. All right, so if it's nice and straight there. Linear. Other questions so far? We'll go through and fill out second order. All right, your rate law, if it's second order, would be rate equals K, your concentration, up to the second order. If we took the integral and rearranged it to get in the y equals mx plus b, it'd be 1 over concentration at whatever time is equal to rate law constant times time plus 1 over your original concentration. Now you have it in that lovely y equals mx plus b form. Love it. And whatever your slope is your k if it's second order. A little more focus, sorry. And then what we graph to see if it's second order will be 1 over your concentration versus time. 1 over concentration, time, and again, R squared, if it's close to 1, when you graph this, that means it's second order. And if it's second order, now your half-life is dependent on how much you originally started with. So you have a different half-life equation. Your half-life is equal to 1 over your rate law constant times your original concentration. Half-life, here you'd have a constant half-life for a first order. It's not constant for second order. So half-life is not constant. It does depend on I guess we can do this. Concentration. And if it's zero order, it would just be your concentration and time and get a nice R squared. And it could be concentration, or if it's a gas, you could also do pressure. 1 over pressure, natural log of pressure, just pressure. For gases, pressure are proportional to concentration. More moles, higher pressure. And that was for zero order. And the rate law for zero order is just dependent on your rate law constant. So this would be a nice little sheet to have, especially when you're working on your homework. On your equation sheet, I'll show you what we have that has to do with this chapter here. They tell you, okay, K is a rate law constant, T stands for time, that's your half-life. They gave you both the integrated rate laws, but they're not in the y equals mx plus b form. You'd have to rearrange them. They give you it, but you'd have to rearrange it. And then they give you, it doesn't tell you, but that this is for a first order. But they didn't give you the second order. Okay, so be familiar with that. And then let's go back to our PowerPoint when you're ready. We're gonna do a few more slides. And then talk about our lab for tomorrow. Change this. Okay, and current slide. Okay, so something we talked about back sophomore year, and something this will be good for you to think about for your lab tomorrow, is the collision model. So for something to have to go from reactants to products, they have to collide. They have to be in contact, because every time you have a chemical change, bonds are broken and new bonds are formed. And it gets that energy or releases that energy only if they collide. So when we're talking about, we're increasing the collisions, right? So the beginning of the chapter was like more collisions, put it in a smaller container, add more reactants, increase surface area, things like that, add a catalyst. And we'll talk about the catalyst here. Actually, we'll talk about the catalyst on Friday. So they need to collide, bonds are always broken, new bonds are formed. And they have to be in the correct orientation. So here's a reactant, here's a reactant. Looks like it needs to line up just like this, have the right energy, not too little, not too much. Collide, this bond forms, this bond breaks, and then they head out. So they have to be in the correct orientation and with the proper amount of energy to cause this breaking and forming. Say if it was lined up with the red, it wouldn't do the reaction. But to go back to the beginning of the chapter, statistically, the more chances we have for collisions, the higher chance it'll be lined up correctly with the correct amount of energy. And you'll see this analogy a lot, like a little putt-putt golf or mini golf. So in other words, there's a minimum amount of energy that they need to collide with. That's called the activation energy. So that's a capital E subscript A, E for good old energy. So just like a ball can't go over a hill, it doesn't just roll up the hill with enough energy. You have to give it some energy, right? It has to have a certain amount to get over. If it's not too much, it'll roll back down. If it's too much, it'll go past the hole, right? So it's got to be that perfect amount. And the reason I think they use this a lot is it looks like our one of these graphs that we do. because this is your activation energy, and we're going to see on the next slide from sophomore year. They had, remember when we did the steel wool? So this one, because there was so much oxygen already there, its activation, there was enough collisions. Bam. The reason we give it a little heat, even though that's not one of the reactants, that gives the few oxygens that are there enough energy to get up that hill. So that's why we give that boost. Or same with charcoal. If I put charcoal in pure oxygen, it'll combust. But we're not in pure oxygen. We have low oxygen, so we light the barbecue, give it that little boost, that little activation energy to get it going. All right, let's go to that graph. So when we are thinking about this, think about energy. Here, your potential energy, the energy this little guy comes in with. It's got a triple bond, some single bonds. It needs to get over this hump to be able to make the activated complex. It's very unstable, not a reactant, not a product. What it is on this graph, I'll go back here in a second. This thing right here would be like your activated complex. Not a reactant, not a product. These are in contact and only last for like a microsecond. But it takes a certain amount of energy to go from here to here. And that's called your activation energy. So your activation energy is from your whatever energy your reactants come in with to the peak, to your activated complex. That's your activation energy. And then we did this in our enthalpy part, the difference between your products and reactants. So here it starts high and goes low. I had to release energy. So this one happens to be exothermic, right? It started with some energy up here, landed down here. So this difference, if you did final minus initial, would be negative. There's your products. Helpful to visualize energy changes throughout the process on a reaction coordinate diagram like this for that chemical change. Let's see anything else I want to say about that. The diagram shows the energy of the reactants and the products, or its difference in energy. The highest point is your transition state. The thing that's up there is called the activated complex. And it's very unstable. And I showed you guys this little guy back in the day. Think of like the green as your reactants. The orange is going to be your products. I have to see if I can do it. Okay, so there's your products. But I had to go through, I had to give it energy. It had to go through this state before it could become products. This is your activated complex. It didn't last very long. It's very unstable. And it's kind of a nice analogy because it's at the top, right? Before it rolls down and makes products. But it had to be this funky, high energy, unstable, activated complex before it could make the products. And then we could do the reverse. Oh, see, that didn't work. It didn't have the right amount of energy. It didn't reach its activated complex or its transition state to go back. And so when you have a bunch of oxygen around, it doesn't take that much versus when there's not. Like right now, we have oxygen, I mean, but it's not 100%. You have to give it that flame. And it's not like because it needs the heat as a reactant, it just gives it that boost. It gives it that kinetic energy to get over the hump. Oh, there it is. So the species itself, this would be the activated complex. It's going to be the highest point of energy during your chemical change. And then the spot on the diagram is called the transition state. But they happen in the same place, if that makes sense. It's like one's that, this is like the noun, I guess. This is the activated complex. And then I guess the other one's an adjective, but where it's at on the graph is the transition state. And then your difference in energy from your products and reactants tells you if it's exo or endo. And so that minimum amount of energy to get over is called your activation energy barrier. So if we look at our Maxwell-Boltzmann distribution, remember we had different temps. At a lower temp, we're looking at the area under the curve. This is your activation energy right here, that barrier. At a higher temp, there's more particles. There's a larger area under the curve that are able to become products. At a lower temp, some are, but it's a much smaller shaded area or a smaller fraction of molecules that have enough energy to get over and become products. And we're thinking getting over, remember, it's that it's contact and the right orientation to make and break the bonds. We're trying to increase those chances. If they're moving faster, this peak broadens and you get a higher area under the curve, more stuff that has enough energy to make contact in the correct orientation and make products. Crosses that minimum energy, which of course has a vocab term, activation energy. There we go. At any temperature where there's a wide distribution of energies. Oh yeah, what I said is going over the next 3 slides. Just going to be repeating it. I guess I just didn't have the patience. So as the temp increases, the curve flattens and broadens, which means there's a larger fraction that's past that activation energy. So some of you guys will be picking temperature tomorrow, right, to mess with. This is why. Or a different lens of looking at why it works out. Higher energy, they can get over that hump. If the dotted line is at activation energy, as temp increases, the fraction of molecules that can have high enough kinetic energy to get over it or overcome that barrier increases. So then it goes faster, right? Because you get more products per second, which is how we do rates, concentration per second, of either reactants going down or products going up. Sorry, I know I'm watching the time. I'm getting very, very, very close. There's just these, I wanted to get to these next 2 slides because that's what's on our last 2 pieces of our homework. Okay, so F is the fraction of molecules under this curve. That's a new little thing. E is just the E on your calculator, the number. R is our gas law constant, but make sure you are using, you know, there's 0.0821, there's different units. Make sure you're using the 8.31 because that breaks down into joules per mole Kelvin. So here's your Kelvin, and this is energy so that your joules cancel. So make sure your gas law constant, you're using this. Make sure your temperature is in Kelvin. And this is so cool because you can figure out what's that minimum energy that your reaction needs to get over the hump. We can solve for this. Yeah, R is gas constant, T, make sure it's in Kelvin. So Arrhenius, we'll see this guy again in acids and bases, he developed a mathematical relationship between your rate law constant and your activation energy. So I thought that was kind of cool. A is your frequency factor. They rearranged the last one. This is your rate law constant. This is your activation energy. That's the 8.31. This is just the number E on your calculator. And then your temperature in Kelvin. And so your frequency factor, A, is the number that represents the likelihood of how many collisions would occur with the proper orientation at that temperature. Last slide. This is what I've been trying to build up for, is the graphing. If you took the natural log of both sides, now it's in that, what we love, our y equals mx plus b form. So what's cool is that you can, from graphing the natural log of, because remember K is different at each temp. So here's different temperatures. If you do 1 over temp for your X, the natural log of the K values at each of those temps on your Y, your slope is equal to your negative activation energy over your gas law constant. We know this is 8.31. This you get from your graph, and then you could solve for X. So you can like solve for the activation energy. I think that's really cool. So if K is determined experimentally at different temperatures, your activation energy can be figured out by getting the slope of natural log of all those Ks and 1 over temperature in Kelvin. Sorry, I know I'm out of time. Let me just show you the homework. Remind you a couple things of the lab. So the homework, couple outlines, surprise, surprise, is you're going to be using those rate laws and see, do you have original concentration, final concentration, original time? Make sure all your time is in seconds. If it's looking for fraction, just pick a number to be your original, maybe 100, and then see what percentage of 100, or 1, and then you'll get a percentage one. Just pick any number if they don't give you a starting number. And then this last part here, it says that this decomposes, and we're using a pressure sensor. So here's some time, and every 10 seconds they took the pressure. The following data are collected. Figure out if it's first or second. So then you're going to graph this. And since you're at home and we don't have time to go over the calculator, just use it on the computer. You can just type in, do time and pressure. Do time, right, and the natural log of your pressures. Do time and 1 over your pressures and see which one gives you the R squared closest to 1. And then this is what we just went over. Is we went, what's the activation energy? That's that very last slide. Change all these to Kelvin. Graph 1 over time in your X. And I think what's the natural log of little k? Yes. And then the natural log of each of these. And then your slope is equal to the negative activation energy over R, which is 8.31. That's why I was in a rush to get to that last slide to get to this guy here. So slideshow will help you with this, and then our notes will help you with the front and back page of that other one. I always have office hours, and I will see you tomorrow. So what you want to be ready for tomorrow, another thing you could do is, as the reaction goes forward, right, our reactants are these guys. Do you want to grind them up or not? There's going to be different sizes. We'll have a scale. You use under a gram for each trial. You probably want to keep that consistent on what you're thinking of doing. What should be happening to the mass of this and your acid as time goes on? Should the mass be going up, down, or not changing as it starts reacting?
Down.
Yeah, going down. Exactly. Because it's being used up to do what? To make the salt water and the CO2 gas. So you could try to measure over time as one of them, right? I mean, that's something. Or, right, we talked about this guy. Gas or products are being made. So that's another way. And then another thing that Chase found earlier actually is we also have these pressure sensors that fit into your Erlenmeyer flask and you hook up to the Vernier LabQuest. And pressure is directly proportional to moles. So if you have a higher pressure, you have more moles. You don't have to do PV equals nRT even. You can just state pressure is proportional to moles. And this is what happened to the pressure. Here's my data. And you can make some conclusions off of that. If that makes sense. So we're pretending like we know nothing about rate laws, nothing about integrated rate laws. We're keeping it simple and just not a lot of math. Just kind of, do you have some data you can collect to show how fast or slow the reaction is going when you manipulate something? You need a control, and then one thing where you manipulated it, and lots of trials. I recommend emailing me your procedure before tomorrow so you can get rolling, and I can give you some feedback. Rough draft. And then your pre-lab is just those 3 questions. They're really simple. It's like, what does surface area do? Is literally one of the 3 questions. Bring that tomorrow and I'll stamp it, and bring a mask. Any questions? Sorry, I totally went over time. I apologize. Okay, I'll see you tomorrow. Thanks, guys.
Thank you, Ms. Fee.